Section 1. Understanding forces within. An introduction. In the world of structural engineering, understanding how forces impact structures is paramount. We design buildings, bridges, and countless other structures to withstand various loads and stresses. Two critical concepts in this field are shear force and bending moment. They help us analyze and predict the behavior of structures under different conditions. Imagine a simple beam, like a plank of wood, supported at its ends. When a load is applied to the beam, like a heavy box placed on top, internal forces develop within the beam to resist the load and maintain its shape. Shear force and bending moment are two of these internal forces. This essay will delve into the fascinating world of shear force and bending moment diagrams. We will explore their definitions, significance, and relationship to load distribution and equilibrium. Through simple examples and illustrations, we'll learn how to draw these diagrams step by step. By the end of this journey, you'll gain a solid understanding of these fundamental concepts and their crucial role in designing safe and reliable structures. Section 2. Shear force. Slicing through the basics. Shear force, in simple terms, is the force that acts perpendicular to an object's axis, trying to slice or shear it apart. Think of cutting a piece of paper with scissors. The force you apply with the scissors is a shear force. In a beam, shear force is the internal force that resists this slicing action caused by external loads. It acts transversely to the beam's longitudinal axis. The magnitude of shear force at any point along the beam is equal to the sum of all the vertical forces acting on either side of that point. For instance, consider a beam supported at its ends with a heavy object placed in the middle. The shear force will be highest near the supports, where the beam is resisting the load's downward push. As we move towards the center of the beam, the shear force decreases, reaching zero at the point directly below the load. Section 3. Bending moment. Twisting and turning. Bending moment, on the other hand, is the internal force that tries to bend or twist the beam. It's the force that makes the beam want to curve or deform. Imagine holding a ruler at both ends and applying a force in the middle. The ruler bends due to the bending moment. In a beam, the bending moment at any point is the sum of the moments caused by all the external forces acting on one side of that point. It's a measure of the beam's tendency to rotate or bend at that specific location. Continuing with our beam and heavy object example, the bending moment is highest at the center of the beam where the load is causing the maximum bending effect. The bending moment decreases as we move towards the supports, reaching zero at the support points themselves. Section 4. The crucial connection, shear, moment, and load. Shear force and bending moment are not independent entities. They are intricately related to the load applied to the beam and its support conditions. The distribution of load along the beam directly influences the magnitude and variation of shear force and bending moment along its length. For a uniformly distributed load, where the weight is spread evenly across the beam, the shear force diagram will be linear, and the bending moment diagram will be parabolic. On the other hand, a concentrated point load will result in abrupt changes in shear force and a more complex bending moment diagram. Understanding this relationship between load, shear force, and bending moment is crucial in structural analysis. It allows engineers to predict how a beam will behave under different loading scenarios and design it accordingly. Section 5. Equilibrium balancing act for structures. A fundamental concept in structural engineering is equilibrium. For a structure to be stable and safe, all the forces acting on it must be in balance. This means that the sum of all vertical forces must be zero, and the sum of all moments about any point must also be zero. This principle of equilibrium is crucial for determining the reactions at the supports of a beam. Reactions are the forces that the supports exert on the beam to keep it in equilibrium. By applying the equations of equilibrium, we can calculate the magnitude and direction of these reactions. Understanding equilibrium and reactions is essential for analyzing any structure, from simple beams to complex bridges and buildings. Section 6. Reactions, the support system. Reactions play a vital role in ensuring the stability of a beam or any structure. They are the forces that the supports exert on the structure to counteract the applied loads and maintain equilibrium. The type of support determines the type of reaction it provides. For instance, a simply supported beam, like the plank of wood example, has two supports, one at each end. Each support provides a vertical reaction force to counterbalance the weight of the beam and any applied loads. Other types of supports, such as roller supports, pin supports, and fixed supports, offer different combinations of vertical and horizontal reactions and even moments. By understanding the type of support and applying the equations of equilibrium, we can determine the reactions at the supports, which is a crucial step in analyzing the internal forces within the beam. Section 7. Mastering shear force diagrams. A shear force diagram, or SFD, is a graphical representation of the variation of shear force along the length of the beam. It provides a visual representation of how the shear force changes at different points due to the applied loads and reactions. To draw an SFD, we follow these steps. First, determine the reactions at the supports using the equations of equilibrium. Second, start from the left end of the beam and move towards the right. Third, at each point, load or change in load, calculate the shear force by summing the vertical forces to the left or right of that point. Fourth, plot the calculated shear force values on the diagram, with positive values above the baseline and negative values below. Finally, connect the plotted points with straight lines to complete the SFD. The resulting SFD will show the magnitude and direction of shear force at any point along the beam, providing valuable insights into the beam's internal forces. Section 8. Unveiling bending moment diagrams. Similar to SFDs, bending moment diagrams, or BMDs, graphically depict the variation of bending moment along the beam's length. They provide a visual representation of the bending effects caused by the applied loads. To construct a BMD, follow these steps. First, determine the reactions at the supports. Second, start from the left end of the beam. Third, at each point, load or change in load, calculate the bending moment by summing the moments of all forces to the left or right of that point. Fourth, plot the calculated bending moment values on the diagram, with positive values above the baseline and negative values below. Finally, connect the plotted points with smooth curves to complete the BMD. The BMD provides crucial information about the beam's bending behavior, identifying areas of maximum bending moment and potential weak points. Section 9. Real-world applications, from bridges to bookshelves. Shear force and bending moment diagrams are essential tools for engineers in countless real-world applications. They are used to design and analyze a wide range of structures, ensuring their safety and stability. From massive bridges spanning vast rivers to towering skyscrapers piercing the sky, and even humble bookshelves holding our favorite novels, these diagrams play a crucial role in understanding and predicting structural behavior. By analyzing SFDs and BMDs, engineers can determine the maximum shear force and bending moment a beam will experience under specific loading conditions, identify critical points where the beam is most likely to fail, optimize the design of the beam by adjusting its shape, size, or material to withstand the anticipated loads, and ensure the safety and longevity of structures, preventing catastrophic failures and costly repairs. In conclusion, mastering shear force and bending moment diagrams is fundamental for any aspiring engineer. These powerful tools allow us to delve into the inner workings of structures, understand the forces at play, and design structures that are both safe and efficient. So, next time you cross a bridge, or walk into a building, take a moment to appreciate the invisible forces that hold it all together, and the elegant diagrams that helped engineers bring it to life.